seconds ago. Yeah, I think what oh what the hell? All right, guys, let's get started. Okay. So today, we're going to continue with the Perceptron. We should be able to wrap it up today. Okay, so it's the last bit of it. Something pretty important, actually. So to kind of motivate it, let's go to the GitHub. Okay. Let's go to Machine Learning Foundations. Remember, it's in neural networks. And then the Perceptron, right? So this is what we've been discussing. So this is you're reading this. We went over, this is the code that I did last week, and we're going to pick up here again today, right? So this is the code we're using, guys. Right, so the key thing that I want you to understand, this little Perceptron code is actually extremely important, okay? And that's why I'm spending so much time on it, because from here we just build up, right? This is, whether you're doing a deep neural network or you're doing whatever you're doing, it's still going to have the same overall structure. It's just going to have a little bit more, complexity. So for instance, this line of code here, as you remember, this is the inference equation. So it's a dot product operation. As I mentioned, some of those tensor operations that we discussed at the very beginning of the semester. And it's essentially just multiplying the x vector, the input, which in this case would be what? The image in your example, right? The T or the L times the weights plus the bias. Okay? So this equation doesn't go away, but essentially it just becomes more complex. It becomes, more functions instead of just one, but they all essentially have the same structure as we go forward. So as we continue for the next 5 weeks or so, this will change. It'll change so much that we'll bring it out and create its own function and then its own class, and because that's the neural network. That's the neural network. All right, multiple layers, complexity, could be even ChatGPT, right? So it's just more complexity. So that's kind of the way it works. We give it an input, we don't know the weights, and then we make the multiplication and predict something. Initially, as you guys know, we've established these weights are random. In my example, they were actually zeros. Now, starting with weights that are zeros is probably not a good idea. For this example, it's fine, but you would really want them to be random values instead of all zeros, okay? And we'll talk about why that is later on in the semester, but just for now, be aware of that, okay? Now, the key question is, okay, we understand that function. Given an image or an input, we multiply it times the weights, get our answer. But the question is then, how do we learn those weights, right? How do we learn them? That's the second component of this, which in this case is just this, right? So this here is called the learning rule, the perceptron learning rule. And it's something that you can't just like randomly change the weights. That would be very inefficient, right? If we had a quantum computer, maybe in parallel, you could generate all the possible weight combinations in the world, try them all in parallel, and then choose the one that provided the best results. Okay, but we don't have a quantum computer. And so we got to have an algorithm that efficiently updates the weights. You guys see that? So how does that work exactly? Okay, so that's what I'm going to talk about today. So how did they come up with this rule? Okay, and the idea is somewhat straightforward, but that's essentially what I'm going to discuss. I'm going to go to the whiteboard for this one, but we just want to know. So the thing for you to remember is that the learning rule, right? The update rule. Let me get my notes. It's going to have a specific format. And I'll write that down, but it's supposed to be weights equal new weights equal old weights plus a term, which is made up of three things. The learning rate, right? times the actual sample times the difference between the predicted and the real. And we'll see that there. So that's broken up here into parts, but that could, that could have been written as one single thing. You can see that here. Learning rate is one parameter. This is another parameter, and that becomes update. And then this update here is multiplied times the sample. All right, so it's made up of three things. And so you might ask yourself, where does that come from, right? And so that's where we're going to derive that essentially today. And I'll give you the intuition as to why that is. But there's really just two ideas there. How we get it is one thing, but what's happening is really very simple. We have a weight, some value, and we need to decide, do I add or subtract to it? Do you guys see that? So am I going to add something or reduce something from the value? And so you need to know, so plus or minus, right? That's the key question, plus or minus. And then the second question is by how much? So that's the learning rate. The learning rate is essentially just like how much do you add, how little, and that's important because it could, if you're adding very little, 0.000001, essentially the weights are not changing, right? If you're adding 0.5, you may be adding too much. You see that? So it's going to change way too much and you never converge, essentially. Okay, so all of our neural networks are going to have some kind of a thing called the update rule, the learning rule. Eventually, we're going to start calling that the loss function. But it's the same idea. How do we obtain the weights? And then just the inference function is just this, it's going to be bigger and bigger and bigger with more weights and so on. Here we have three weights. DeepSeek, which is a competitor to ChatGPT, currently has 671 billion weights. Think about that. All right, so 3 versus 671 billion. All right, so, but that's the idea. All right, so I'm going to switch over. So I've motivated that I'm focusing on this part, and where did this learning rate come from, right? And the key question is, really, do we add or subtract from the weight value? So I'm going to create now, I'm going to stop sharing. That's what I want to do. I'm going to switch to the whiteboard, new whiteboard. And we're going to think about this problem through and I'm going to put it in the context of the T's and the L's, essentially. So let me grab my pen here. All right, so let's go. So this is the perceptron. Bring up the pencil. Perceptron. And what we want to figure out is the learning rule, basically. So as you know, the motivation is you have images, right? And you have a T, or you have this T, right? Those are essentially the two cases you have for a T. And we want the label to be something like in our little apparatus device, right? We want the needle to go in that direction, right? And that just means it's something like 1 or plus 1, right? The class that we are trying to predict. Okay, got it? All right, so that's one idea. If we have the other letter, L, or however you did it, right? Something like that. And essentially, we've got our device that goes in that direction, and that's a -1. So that's the class. Or it could be a 1 and a 0, depending on how you define it in the code. Okay. So let's simplify this a little bit now to, instead of an image, I'm just going to have something that is a vector of 2 so that we have 4 possible combinations, right? So if you remember, these were images that are 4 by 4, which create a vector of size 16. But just so that we can visualize this a little bit better, I'm going to simplify this to just be, instead of 16 switches, it's just going to be 2 switches. You see that? So, and see all the possible combinations of. Okay, so I'm going to do add page here. Here. All right, so I'm going to think of this as 2 cases. I'm going to think of, so remember, I have 2 switches, right? So what are the possible combinations here? I have the 2 switches are off, 1 switch is on and the other one is off. So like this, so the first one is on, this one is off, or this one is off and this one is on. Or I have this like that, right? So all of them, both of them are on. Okay. So again, we can define this problem. This is, we can say that if both of them are off, then the class is like this. And otherwise, the class is going to be like that. Okay. So that's a scenario, right? Another scenario is that we can have this, 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 and that. And here we're just going to say this is the XOR problem, which is really important in neural networks. Essentially, XOR means that we want to differentiate between when only one is on and when both are either on or off, right? So that's XOR. So this would be something like that. And then this would be like that, like that, like that, right? So these are different individual problems that we can have, and we'll come back to this one. So let's visualize this now a little bit more. Okay, so let's think of plotting this data, right? So I'm going to try to plot this XOR into a graph. Page. Okay, so plot it. Okay, we're going to say that I'm going to need the data here. So I'm going to say F, S, and this is going to be first and second, right? So first and second. Okay, so I have so we're going to try to graphically visualize this and try to think of that prediction equation as a line that we are creating, all right, that separates the data. Does that make sense? So this has values -1, 1, -1, and +1. Okay. So we're going to try to plot these values. So we've established, so the combinations for 2 are a binary is 2 off, 1 on, 1 off, 1 off, 1 on, 2 on. And in the XOR logic, the XOR. You have to understand that in the very beginning, when they were built, so why XOR? In the very beginning, when they were building neural networks, what did they have already with computers? They had circuits that had basically these operations in binary, right? So all the binary operations, and they were trying all the binary operations instead of using an actual, they were thinking actually, instead of building the circuits as we have them, what if the circuits could be neural networks? You see what I'm saying? So that was kind of where the thought was back then. They had, you know, what we know of computers today that are binary, and they perform binary operations. And so they were thinking almost, could we replace that with just neural network circuits? And so they started testing all these binary operations that you had in electronics. And it worked for many. And then they got to the XOR operation, the XOR binary operation. And that's kind of something that's really important because it presents some challenges. All right, so let's think about this one. So in the XOR operation, and again, this goes back, if you remember, to your truth tables, right? So you probably did this in discrete math or somewhere like that. You remember that you had a true table. True, true, false, true, true, false, false, false. You know what I mean? So that's what I'm talking about. So the XOR essentially says, whoops. Do you see that? So you all agree that that's the XOR operation. Okay, great. So now let's plot this on the graph. And essentially what I'm saying is build a classifier that can separate this one and this one from this one and this, right? Because I'm saying this is one class and this is the other class. Do you guys see that? So we're going to try to build a linear classifier that can do that. And the way that I understand it is we have a Cartesian plane and we're just going to draw a line that separates it. Okay, all right. And we've established, and this also gives us the relationship between a line here graphically and the equation dot product x times w plus b that we have in our Python code. Because as you know from your high school algebra, that is the equation for a straight line, right? You guys know. All right, so let's think of this case. So this is a little graph. So I'm going to actually plot these here to kind of indicate what they are. So I have here two switches on, right? So that's this case. So that means +1 and +1. Do you all agree? 1 and 1? Okay, great. Then I'm going to do the next one at the bottom here. Right? So this one means +1, but this is the other value, negative, right? You see that? So that's why it's +1 -1 is the scenario here. Okay? Then we do the next one. Why? Because this one is both off, so negative, negative. Yeah? And then finally, then what is this one here? This is x, correct? So in this case, we have x is negative and y is positive. Okay, so remember fs, so this is the f-axis, this is the s-axis for first and second. Do you guys see that? Now we've established that the classes are, and I'll change color for this to blue. So we've said that whenever you have something like this, right, that is class 0. And then when we have this one over here, that is also class 0. So that means that when we have this one is class 1, and when we have this one is class 1. Do you guys see that? So that the XOR problem is very difficult and presented a problem in the beginning because what we're trying to do intuitively, we can think about this. I'm going to use green. When we have y equal w x plus b like that, we can think of that as being a line. So we are trying to figure out w and b that produces a line that separates the samples. Do you guys see that? But what's a straight line that will separate this data? If I draw that, imagine, sorry, that's not a straight line, but imagine it's a straight line, right? That separates this one from these, but we have one error. You guys see that? Okay, so what's another? Is there a line that will separate this with zero error, basically? No, right? There is none. So if I do a line like this, I got an error. If I do a line like that, I have an error. So I always have an error, right? So this problem, you could argue, is not linearly separable. In fact, the only way to separate it is to build something like that. Do you see that? That would provide a separation. Another way of visualizing this is to imagine that you're building multiple lines. You see that? And then that would allow you to separate these from these with with zero error, essentially. So that's your goal, but just a simple straight line will not be able to separate with zero error, okay? So this motivation is kind of where you start. So this is one of the problems with the original Perceptron, okay? The original Perceptron, the one that we're building today, was really great, but somebody argued that it cannot solve the XOR problem, okay? So what do we need to solve the XOR problem? We need models that can create, now this one, we've established that can create a line, right? So this, we'll see in a second that the Perceptron can create one line, but unfortunately, one line is not enough to separate all the data. So that's why we build on top of the Perceptron to have multiple Perceptrons together to create more complex neural networks. So the next stages are going to be to create something called a multi-layer Perceptron. And what does that mean? It's going to have more neurons, it's going to have more layers, more activation functions, and essentially, eventually, it will be able to create something that looks like that. Does the intuition make sense? So this function here just becomes more complex so that it can create a more complex separation line, which is no longer linear. As you notice, this is kind of made up of curves and so on. Got it, guys? Do you understand this idea? All right, so I have to start here because I have to say what the limitation of the Perceptron was. Okay, so the limitation of the Perceptron was this. It was invented, it was very exciting, everything that was going on. It was going to replace all the circuits in computers with neural networks until they hit on the XOR problem. And the XOR problem, the Perceptron cannot solve, but obviously other neural networks can. But this also graphically allows me to connect this to just a line. Do you see that? So now I've given you like the basics of it. So the Perceptron cannot draw this as is, right? So we can only draw a line essentially, and the results are not going to be perfect, right? So it's going to be a limitation, okay? Now remember that a line such as this, and we will create a Jupyter notebook in a little bit just to kind of illustrate how that works, right? So it's essentially the relationship between what? X and Y. Do you guys see that? So that's essentially what we're doing here. So we have an X, and it's going to tell us what the Y is. Okay, so that's why we have when we have the X, right? The X input, we're going to predict that Y value. So it's like I have this here, and once I calculate the W's and the biases, I can tell what this value is. Does that make sense, guys? Okay, and then we use that information to build a classifier that can separate the data with that objective. Okay, and so, but all of that depends on the learning rule. And so that's one of the things that we need to derive is why, how did they invent that learning rule? All right, so we've made the connection, right, between the line, we have some data, and the equation. Okay, so now let's move on. Okay, new chart. So the next thing is, we can write the equation as being output equal W1 X plus W2 Y plus B, right? Assuming we have those two parameters. So what is traditionally what you do is you set this value to be something like 0, all right, so that you can move around the terms. So I'm going to do W1 X. This could also be like less than or greater than, but it's the same. So let me illustrate that. So this could also be like that, right? So it just means values greater than 0 or values less than 0. And that kind of illustrates the idea of how the perceptron works, right? To assign one class or the other. But to keep it simple, let's write this as equal. All right, so 0. So then I have W1X plus W2Y plus B, right? So the same idea of the values, and we have these parameters that we are learning. Now, the good thing about having something like this is it allows you to move the terms and see the line. So here, I'm just going to move the terms. So I'm going to say, I'm going to rewrite this a little bit. I'm going to say W1 X plus W2 Y plus B. And then now I'm just going to move it. It's just rearranged it, right? So once I rearranged it, I can further modify it as W2Y equal what? I'm going to move so this W1X, I'm going to move it to the other side. So that just means minus W1X, right? And then the B is also moved to the other side. So that becomes minus B. Do you see how it's starting to take the shape of a line? Oh, yeah, go ahead, sir.
Yeah. W, okay, this that.
The weights.
Oh,
W1, I just made it, I'm trying to tie it back to the graph that I had here, right? So if I go here, so remember what I said here, this equation, which is the inference equation, you agree from the perceptron? Yeah, the inference equation. And this is just the line that I intuitively gave you that we're trying to figure out to separate between the two classes. You see that?
So where do weights come into play with that?
With the line?
Yeah.
That's what I'm trying to do right now.
Oh, so is this like adjusting?
I'm moving the parameters so it looks more like a line.
And is the line representative of the weights?
Yes, the slope.
Ah,
That's where I'm going.
okay. And
we'll graph it. We'll
yeah.
graph it in a second. So we'll do it in Python also. And you'll see that it is a graph.
Okay.
But that's what I'm trying to say is think of the inference function, which is the one in the perceptron as this. You agree that NP dot, right? Yeah. We're trying to learn these weights and biases. The weights and biases just provide a relationship between this X and this Y. And what essentially, if you use your imagination, think of if let's say that I started playing with the W's and the biases randomly, changing, what would happen to this green line here? We just start rotating. You know, like you can spin it, move it, whatever I want with it, because it is totally dependent on the weights and the biases. You see what I'm saying? So because I changed the slope of it, right? It just does that. I change the bias, it moves around. So that's essentially what I'm trying to show you is that this is the inference equation that we're trying to learn. We're essentially trying to learn the weights and the biases, but those determine this green line and how it moves. It's always a straight line. It's just going to move. So I just kind of wrote this as X and Y. So it's X and Y here. Okay. So I'm going to go down to where I was here. Okay, so I have my function output, which given xw and yw, those values, I want to predict what the class is. I just set it to 0 for convenience. I'm rearranging it. And now you can see, as I continue with it, right over here, I just want to write it in terms of y. So this is going to be then what? Minus w1 x, sorry, x divided by W2. Do you see that? I'm just rearranging the terms. And this other one is going to be minus B divided by W2. Okay? But essentially now it's starting to look like a line because what do we know about a line? It is mx plus B. Right? And that's this M, just replace that M with W. You see that? And that's the graph that we know creates a line, essentially. All right, so that's the connection. So I just rewrote all the term in terms of this. So let me just... Okay. All right, so I have that. So this equation becomes, just to simplify it further, minus W1, W2, X minus B W2. And it just shows that it has, plus, minus, doesn't matter, but it just has that basic form of a line. So intuitively, you can see the connection between the weights and the biases that you're learning and the shape of that line until you arrive at one that separates things perfectly. Okay? But that's what we need to, so we're adjusting them. We need to have some kind of a learning rule that moves it around, right? So for instance, going back to the example over here, this one. So what's the thing that allows me to decide what line to use? Well, let's take an exaggerated case, which is usually what's the best. Let's say this plot goes out to infinity, right? So the first set of the weights and biases that I come up with give me that line, that's a terrible line, right? It gets almost everything, or it gets a lot of errors, essentially, right? So that's worse than the green line. Do you agree that the green line is better than the yellow line? The green line has only one error, right? So it's trying to separate between ones and zeros. Okay, so 0 and 0 on this one side, 1 on that side, but unfortunately, it gets this one incorrect. Do you see that? What about the yellow line? So nothing on this side, and on this side, I guess it got 2 correct, 0 and 0, but it got 2 incorrect. Do you see that? 1 and 1. So this is how you know which line is better. This one gets 2 wrong, the yellow one. The green one only gets 1 wrong. Do you guys see the difference? Does that make sense? That's the learning rule, right? So you're comparing the predicted to the real, and you're trying to minimize that. Okay? So when we find a set of weights and biases that gives us a yellow line, 2 errors. Error equal 2. We want to minimize that, okay? I find another set of weights and biases that gives me green line. Green line has only 1 error. So 2, 1, I minimized it to 1. Make sense? That's the objective of this whole thing. Always, right? To find a function that minimizes the error. Okay? So that's where that's coming from. And how do you, so how do you know that? How do you do that? You need to adjust the weight. So we have this function with weights and biases that are some value, and we get yellow line, which gives us error 2. So that's not good. We need to minimize that. But the question is, how do we adjust the weights and biases? That's the really critical aspect. Do we add to them or do we subtract to them? So that's essentially the problem. Okay, I'm going to go over here. So a couple of things. So we've established with that equation that this is essentially a line. It's the line equation, basically. And by calculating these weights and biases, you can see that M is changing. You guys see that? So we try, this sequence of weights and biases, we have one M, we have another set of weights and biases, we have another set of parameters, and that line is just moving around all over the place. Okay? So that is the line equation. So now let's take an example of what I mean by this. So let's take some values. I'm going to create a new whiteboard. Okay, so let's imagine now the equation, right? So I'm going to use this, oops. So I'm going to use y hat, right? And that's going to be x0, w0 plus x1, w1 plus b. And now let's imagine some values. So we're going to have one snapshot where we actually have values. And let's see the whole process. So I'm going to do here, I'm going to say that we know that x0 is going to be equal to -1. X1 is going to be equal to -1. Y, the predicted value, is going to be equal to -1. Okay, so we have that. And then we've also learned the parameters in this scenario. The parameters are going to be W0 equal -1, W1 equals 1, and the bias is going to be equal 1. Do you guys see that? So now, as you might imagine, what I'm going to do is I'm going to plug all the values in the equation. All right, so let's try that. So y hat equals x0 minus 1. Do you guys see that? Then I have W0 is also -1 plus x1 is -1. W1 is 1. And the bias is 1. Right? So we have a set of x's and y's that are the real data, and we have a set of parameters, w and b. So we do this calculation, y hat, that's going to be, this is 1, this is -1, and this one over here is 1. So the predicted value is going to be +1. Okay, that's the predicted value. Okay, we know that the real value is actually -1. That's this one, right? That's the real value. the real label, if you will. We have the predicted and the real label. So we're going to say here, predicted, real. So predicted is y hat, real is just y. That's the notation that you will see me use for the rest of the semester. So a lot of this notation is new to you now, but it's not going to be new in 3 weeks, and it's going to be pretty consistent. So this gave us +1, but the real value is actually -1. Do you see what I'm saying? So they are different. Actually, it did not predict what it was supposed to predict, right? And so what we do now is we're going to have this idea of error, which is very common in all of machine learning, right? So you compare the predicted to the real. So we're going to denote this as y minus y hat. Do you guys see that? All right. So then how does that evaluate? Error will be y real is -1 minus, and then the y hat, which is the predicted, is +1, right? Do you guys see that? So this is what we're always going to be doing. So now I'm going to do error. So that is -1 minus 1, which is equal to -2. Very good. -2. Thank you. -2. Make sense? A lot of the time in something called MSC, you square this to get rid of that negative effect, right? Because sometimes, it could. So we're just going to square this, and as long as we're consistent, it's fine. Okay, so as long as we're consistent, it's fine. So I'm going to continue this. So just remember this: error equal -2, or actually, I'm going to write it here. So I have it. So then all we have to do is error -2 to get rid of that negative. We square it, and so that becomes error equal 4. Got it? This is essentially how all of machine learning works. You got that equation, you got the real values, the weights and the biases, you do the computation, you have a predicted value, you compare it to the real value, take the difference, square it. That's your error value. Yeah, go ahead.
So is that box a continuation of?
Yeah, I ran out of room here, so I wanted to keep going down.
Oh, okay.
Yeah, so it's this going down. Yeah. The value is 4. Yeah, sorry about that. But that's essentially, and this is important, okay? Because I have an error value, okay? And that's the feedback that you get, okay? So now I need to decide, okay, that's an error of 4. What is my goal in this machine learning problem? I want to have a perfect prediction, right? So perfect prediction means that this value of 4 needs to go down. I need to minimize that 4. And how do I do that? I need to do that by modifying the weights and the biases, the W's and the B's. Everyone with me so far? All right, great. So let's go ahead then. I'm going to remember this equation because I'm going to repeat it again. I'm going to go here. Okay. So now, same thing. So the last value, let's just write it down, was 4 from the previous page, right? So this is coming from the previous page. It is -2 square, which gives us 4. All right, here we are. That's our error. Now let's change the values a little bit, but the same equation. So we're going to say that x0 is -1, x1 is -1. Okay. Y, the real value, the label, is -1. Okay. Have that. And the W's, W0, W1, and B are going to be the following. So B is 1, W1 is 1. Those are the same, right? So if I go back, this is what's important. Obviously, this is not going to change because it's training data, but this is the parameters that we're trying to change. So let's remember W0, W1, and B. Let's go back to the previous example. Here. They were -1, 1, 1. -1, 1, 1. So they were -1, 1, 1, the previous ones. The new ones, these two are still 1, and I'm just going to change one of them, the W0. Instead of -1, I'm going to change it to -0.9. Do you guys see that? Essentially, what did I do? I decreased it by 0.10. Do you guys see that? That just decreased it. So that's what the neural network would need to do. It needs to change these parameters, reduce it by a little bit or maybe add by a little bit. And that's the question. What do you do exactly? Which one of the two do you do? And so, but let's see the effect. So now it did the update, changed from -1 to -0.9, right? It did the change in the update rule, and now we recalculate everything. So I have y hat, x0, w0 plus, this should be x0, x1, w1 plus b. Do you guys see that? So then I do y hat. So x0 is -1. W0, okay, here's our new value. So that's going to be -0.9 plus x1 should be -1. Okay. W1 is 1 plus B is 1. Got it? Everyone with me? All right, so let's recompute everything again. So I'm going to do y hat. This is the predicted y. So this one should just be 0.9, right? So negative becomes plus, so that's 0.9. This one is just negative, so -1. And this one is +1, essentially. So now the predicted value, y pred, is just 0.9. You see that? So the neural network will always do this. Adjust the weights, predict again. Okay, so what do we do now? We calculate the error. I'm going to change the color for this one. So error is going to be what? Y minus y hat. Remember, y is the real value and y hat is the predicted value. So we can do this here. I'm going to do error. So y hat, or sorry, it was just y is going to be this one, right? That's the real value, so that's -1. Got it? And then now minus y hat, which is the new predicted value. So that's 0.9. 0.9. You add these two together, what do you get? -1.9, correct? So I'm going to do error. -1.9. But in the previous example, notice that I squared it, remember? So I could get rid of that negative effect. So make sure to be consistent, like to say apples to apples, that you also square it. Okay, so then now you have essentially your error value is going to be this value squared, which is 3.61. Do you guys see what I'm saying? So let me write it over here. So I'm gonna kind of like write it here. 3.61. So what do you conclude from that? Which set of weights is better? This set of weights or the previous set of weights? And why? Yeah, please. This one is better. This set of weights. Why? Lower error. Do you see that? That's it. ChatGPT or this, they work exactly the same way. There's only one learning mechanism for all of deep learning, and it's this. Like only one. There's no like, there's hundreds of architectures. There's only one learning approach, and it is this one. You change things, like you'll use something called cross entropy instead of MSE, but still you take the predicted and the real and minimize, or something like that. If you're doing a model that receives rewards, you maximize the rewards, but it's essentially the same idea. So this is what I wanted to show you. So mechanically, we have seen how this works. You know that the first set of weights gave us 4. That was the error. We know that we have a goal. Machine learning always has a goal. And so that's why some people say we got to be careful when we train AIs and the goals that we give them, because let's say that you gave AI the goal of make sure reduce traffic in a city like Chicago. And AI thinks about it and is like, okay, how do I reduce traffic? Well, if I kill all humans, there is no traffic. Do you see what I'm saying? So you have to be careful with those goals, because if you just tell it reduce traffic, that's an efficient way of reducing traffic to 0, right? But it's just going to do that one goal and optimize. You see what I'm saying? So that's exactly what machine learning algorithms are always doing. They're trying to optimize towards a specific goal, in this case, to minimize the error, essentially. All right, so hopefully you understand then that this is how we keep track. We know that this is a better set of weights because we got this one. So at this point, what you know is that you can I kind of randomly just went from -1 to -0.9. But we have to have a smarter way of doing that. Do you guys see that? Right? We have to have a smarter way, because otherwise, how do I know? Okay, I did -0.9, but what do I do with W1? Do I do 1.10 or do I do 0.9? What do I do with the bias? Do I do 1.10 or 0.9? Right? So how do you update all of these parameters efficiently? Right? So, but right now you understand like the objective. The goal is to minimize the error, and you understand that the way that you're doing it is by changing these weights, and you understand that these weights intuitively translate into, changing these weights translates intuitively into translating some kind of a separation line that separates the samples in an efficient way, mathematically speaking. Okay. So now historically, this is where, like in the 40s, people like Rosenblatt and Widrow, they were like, okay, how do we do this efficiently? Think about it. They're like standing on a whiteboard. We get it. If we minimize that error by changing those parameters, we will arrive at neural networks that are kind of smart, that can do the task. But we need some kind of an algorithm that will do that, right? Okay, and so that's what now we can jump to the perceptron. where the perceptron had something like this. Let's say I, because this WI represents Y0, Y1, right? And then we also need an update for the bias. But let's say we have 3 weights. So we have W2. Do you see that? So we'd have W0, W1, W2. So you just generalize to be WI, which is the weight, equal to WI minus or plus the learning rate times XI times Y minus Y pred. So Y real minus Y pred. This is the formula for the perceptron, the learning rule. Okay, that's like I coded this in the anaconda example, but where does it come from? Do you guys see that? Does that make sense? So in the code, you have this. And essentially, before we had the W0, for instance, was 1, and then I tried 0.9, right? So that means that I took 1 minus 0.10 and arrived at 0.9, right? And it basically then, the perceptron says this is the learning rule, but how do we figure it out? Okay, so let's break it down into the parameters. So we know that we have this value LR, that's called the learning rule, and that is always going to be some parameter that you define. So usually I think the most default one is 0.001. Okay, it's just the value that you're adding from your, so whatever it is. So you have W I W1 W1 minus this value always. You define that. It's kind of a parameter that you set for your algorithm. And what you need to figure out is really this. Okay? Are you going to add or subtract from this? Okay? So how does that work then? How do you figure that out? So this is the part that's a little bit tricky to understand. How this was derived, essentially. So when you have a function that is like this, where think of it in this example. When you have a function that is like this, you're essentially having a relationship between, you can rewrite this as, I'm going to replace this y hat. I'm going to replace this y hat with the actual formula. Okay, here we go. I'm going to simplify it to just x1 W1 plus B, right? Just think of it that way. Okay, so you can actually then create another plot. This is different from the previous plot for the line. This is totally separate, which is a relationship between E on this axis, so this term, and the W1 on this axis. Okay, so think of it that way, right? So if you have you're going to have an equation that given W1, it gives you E. Just like before, we had an equation that given X, it gives me Y, right? Because I figure out the parameters of M and B. That's one, that one equation. we have another one. So that's why I always keep saying there's two functions in machine learning, the inference function and the objective function. Okay. So for this one, we plot the data and a line in it. Does that make sense? So that's one equation and its graph. And now I'm going to have another equation and its graph. Okay, which is plotting something else. So when I give it, you can almost ignore X and B here. You can almost ignore these. These are like parameters in the equation. The thing that matters is that whenever you give it W1, it predicts this value E. Do you see that? So for instance, so then the question you might ask is, okay, great. I understand that I have this chart where I have E over here and W over here. You give me this W1 and I need to give me a value for E. So it's plotting the relationship between the error and the W1. So just like I was doing before, right? So essentially in my previous example, here, essentially, I changed the W0, remember? Minus 0.9, and it gave me this 3.61. Do you guys see that? And before, this was minus 1, and it gave me a 4. You agree? So notice that all of this happened in relation to this error formula, right? I went from 1 to 4, and then from minus 0.9 to 3.61. So I'm able to plot through this equation that relationship. And that was consistent. So now think of it intuitively. Here, as me plotting. So I have this, right? The relationship between E and the W. So if I give you W1, so what was it? If it was, what was it? Minus 1 for W1, what was the value? 4? Right? Do you see that? And if I give you minus 0.9, actually, this would be here, right? Not there. Minus 0.9, then it gave me 3.61. So it's almost like it went like this, and it went like that. And then if I had this, it went like that. Do you see that? So I'm given one value, I can plot the other one. So then what you might ask yourself is, this equation here actually represents a function. Just like this equation here represents this line, and we just need to know the slope and the bias, and we can draw it. This one over here, this little square thing, is called a quadratic function. And it has a very specific shape. Which looks like what? It looks like a bowl. So it's got the bowl, the famous bowl shape, like that. Do you see that? Why is that? I mean, if we look at, we can do this in a very simple example. So x2, right? We have, if it's negative, minus 3, and 3. So if it's 3, goes in there, it's 9, right? So it's going to be 9 over here. Say that's 9. If I plug in minus 3 square, that is also 9. That's going to be here. And I can just keep doing that for all the numbers, and it just looks like a bowl shape. Do you see that? So it's got a specific it creates this relationship between the weights and the error. Okay, that has a very particular shape. Okay, so the trick is then the intuition is, if you look at it, if we go back to the previous one, so what is the objective with the error value? What do you want the error value to be? This is actually the value, right? So this was 4, and this is 3.61. What did we say about that error value? Which one was better, the 4 or the 361? The 361, right? Yes, whichever one was closer to 0. So if you look at this graph, it actually tells you what you should do. If actually the way that I drew it, if you look, if I make this number go further to the right, actually error will start to go up. Do you see that? If I make this W go further in that direction, error will go up. So really, actually, in the way that I drew this, it tells me that this W1 is actually the bottom of that function bowl. And that's essentially the best W1. And I'm not going to be able to get that error to go further down, given the equation. Do you guys see that? Do you guys understand this idea? This is critical. It's like critical to understand this. And the beauty of it, though, it doesn't change. This one idea is not going to change. The functions here will change. But it's always going to be the relationship between these weights and the error, because we capture that through this little function of predicting or of comparing the real minus the predicted value. Okay, so let's draw. Are there any questions before I continue? So that's why it's going to be called stochastic gradient descent. So the algorithm is actually about minimizing this function that we capture. So let's draw it out a little bit more clear. I'm going to draw it out a little bit more clear. So one thing that I want you to memorize if you have to. In deep learning and neural network, there are 2 functions and 2 graphs. They're related, but they're separate also, right? There's the inference function. So I'll kind of summarize here. Very important. Write this down, please. There's the inference function. Okay. That's going to be just your prediction. In its simplest form, W times X. W times X plus B. Okay, this is one plot of the data. Right? Let's say this represents a line, and the line is trying to separate samples, right? And we control the shape of the line with the W's and the biases. Okay, and I'll do Y hat to indicate that's the predicted value. Then there's a second function, which we can call the objective function or the loss function. I'm just going to say objective function for now. Again, if you get confused, the exaggerated case that I gave you, build an AI that reduces traffic to the minimum. Sure, I'll wipe out all humans, right? And I do it because that's the objective, minimize traffic or whatever it is. In this case, we want to minimize error. So essentially, we write it as, this is the error, right? Which is going to be Y real. What is Y real? Y real is not even a function. It's just a value. 1 or -1 or whatever it is you're using. So actually, it's just a number. This one is Y hat. You square it, and that's what makes it a quadratic function in this case, to have that bowl shape. But remember, essentially, just like this function creates the relationship between X and Y, This function creates the relationship between this and error. So I'm just going to rewrite error as what? As this guy over here. You see that? So I'm just going to plug, see y hat. So I'm just plugging this one in there. So I'm just going to, instead of y hat, I just plug, I'm going to actually use a different color here to kind of see that. I'm going to plug it in there. So I'm going to say W times X plus B. My battery's low. Yeah, why is my battery low? Let's see. Oh, there we go. All right. Hopefully it'll last. I don't know why this won't turn on. So I don't think it's charging. Anyway, sorry about that. So let me change to red again. So I'm going to erase this just to be consistent here. This is probably like the most mathy part of this whole class. So the point is, I really want you to understand this because this is throughout. Okay? So squared. All right? So all I did is I plugged this function in there. And remember that what we're modifying is the W's to reduce the error. So that is the relationship we are capturing. And then this has a graph as well. Just that this graph is the relationship between error and just that parameter because it's really W, right? W is the parameter that we're changing. Do you see that? But that relationship cannot be like this function, error, that's written like this, does not write, that function. That's not the function that's there for this particular formula. Or I'm going to do this. If you guys remember in your trigonometry courses when you took them, sine looks like that, right? So you have a sine and it has a particular relationship, a line, every function has a particular shape or form. This equation here, x squared, is called a quadratic. It's fundamental to understanding neural networks. And it has the traditional bowl shape. So now, okay, right? You know that as you're modifying these W's, your goal is to reduce the error. So now let's look at another example. So let's say I'm going to switch color here to green. Let's say that I pick this W, whatever it is. So what do you know about the error? Is that one, right? That's what you know. You pick that W, that's the error. Okay. I try another one. You're randomly doing this, by the way. So you're just like randomly changing the W. So now I pick this W. What do you know about? So that's now this error. So it's actually error went up. So that was a bad move. Then you pick this one, this W here. Okay, some improvement. Now error went down a little bit. But what are you trying to do? You're trying to arrive at this point, right? Because when you get to that, that gives you the lowest error possible, and you have solved your problem. You have minimized the error by playing with the values. Do you guys see that? That's it. Like there's no more going on here. What's going to happen with the neural networks is that this curve is going to take another shape because there's more complexity in the equations. This is the most basic idea of it. So now I give you this question. How do you generalize here to find, so your goal is to get here, right? To the lowest E, and you have a W here. So the question is, let's say that you were here. Let's say that you picked that value, right? You pick W1 randomly, which you do in the beginning, and you're here. You know that this curve goes down, right? So you as smart people, right? What would you say you would do? What should you do? Should you so think of how this works. So if you add a little bit to W, it's going to go in that direction, right? Because you're adding. So it takes you there. And if you subtract something, it's going to take you to there, right? So which way do you go? Do you go this way or do you go that way? What's your simple, right? You go to the left. You go to the left. Exactly. Why? Why do you go to the left?
You want to get closer to zero.
Yeah. And getting closer to zero means going down in this curve, right? Do you agree? You're going down in it. So that's where, so I say that because that's where the name gradient comes from. The idea of gradient is like the connection to being in a mountain range. You're going down the gradient. You see what I'm saying? Guys, so you're imagine you're like a hiker and you're at this point in the mountain and you look at it and you're like, I'm going down. Get it? That's what the objective is. You want to go down always in these graphs, and that's where the name comes in, gradient. So the question is, obviously this is not a mountain. These are conceptual things in our head, but could there be a mathematical way that we could discover that? And there is, as it turns out, from calculus. There is a thing that allows you, and this is where I'm going to throw in the last bit of how this works, okay? So hopefully intuitive, you guys understand that our goal is for error to go down. So we want to go down this function. Where if we are at some point in it, we know that we want to take a step down from it, not a step up, when we are at that point in time. So now let me generalize to what calculus says, right? So let's think about that idea, because this is what Woodrow actually in the 1950s discovered in a very elegant way. And that's where the learning rule comes in. So they said essentially the following. Let's say that you're in imagine, just to kind of exaggerate, the function looks like this, right? And if you're here, intuitively, you want to go down, right? You don't want to go up because you understand that this is the error and you're trying to minimize. If you randomly pick this value, okay, you kind of don't know because you're at the very top, but you should go down. So you might choose to go this way or that way. If you fall here, you want to go down. You don't want to go up, right? So you don't want to go up. Now, you might argue, okay, but I want to go up here so I can later go down because I know this is going to get me to the bottom of the whole thing. This is a hard problem that is unsolved currently. Currently, the algorithms only know that if they're here, they're going to pick to go down. So they're not smart enough to say, I need to go up here so that I can further go down to the very bottom. But that's why you do this randomly. So in multiple times. So now what I'm saying is you do it one time here, but another time you fell here. Lucky you, because when you fell here and you start going down, you'll get to this minima, as it's called, versus this minima. So in one iteration, you get to this minima. In another iteration, you get to this minima, and you are going to know that this one was the lowest. So you'll pick that one as the set of weights. Remember that at the end of it, oh, sorry, my battery and let's see an outlet here. Oh, there is. Is
This power strip over was up one.
oh, was it? Did you fix it? Was
Yeah.
Oh.
That was up one.
oh, all right. Thank you then. Yeah. All right. So I think the computer is also it's charging, right? Yeah. Okay, great. Thanks, Taylor. Yeah. All right. Awesome. Yeah. So as I was saying, right? So the intuition then is the here it is. All right. So the intuition is the function, you fall somewhere in the function, and at that point in time, you kind of decide I'm gonna go down or up. Right? That's the gradient part. Gradient descent, in fact, is the name of the algorithm. Stochastic gradient descent. You're always trying to go down. So here, let's say that you fall here, right? For instance, you're going to go down. When you get to here, all you have is to go up. So unfortunately, the algorithm gets stuck there. And that's called a local minima, not the global minima. What does that mean? It means that your weight is selected to be this one, and that's not a great weight. So if you, for instance, were investing in the stock market, what does that mean? It means that you probably lost $1 million that year because you just picked a set of weights that was not optimal. But if you get to this set of weights, you have a better algorithm and you make $3 more million that year. That's kind of how you can think of it. All right. So hopefully what I can tell you is the problem is we have a function. Now, this is a function for neural networks, but let's go back to just a perceptron, something simpler. We know that that equation is just quadratic little function. We know that this is where it's optimized because that's where the error is. We know that this axis is in terms of W. And we know intuitively that if I fall here, right, I wanna go down. And if I fall here, I want to go down, essentially until I get to that point. So you intuitively know this. But how do you actually compute or calculate something like this? So this is where Widrow, that gentleman in the picture, they thought about it and they were like, wait a minute. Calculus gives you this. Calculus cannot give you everything, but calculus can give you, for this point, information to decide if you should go up or down. And so that's what the derivative does, essentially. So the derivative, so let's go there. In calculus, you have any function, right? And you can take the derivative of that function. So that's like saying the derivative of, let's say, of error, because that's the function, right? So remember, our function is what? Our function is error equal y minus y hat square. That function. It just so happens that that equation gives you this function in terms of the W. So then he says the partial derivative, actually, of error in terms of the weight gives me the information that I want. And this is something that is just invented by Isaac Newton, right? In calculus and everything. So they just made the connection between something they needed and some technique in math that already exists. And this is why we need tools like Torch and TensorFlow, because they actually compute these gradients for us. So all the calculus is done by the library. We're not going to have to do it. Yeah, go ahead, please. Which character? This one? This one? This notation means the partial derivative. So I'll show you what this is. This is just for your FYI. but essentially I'm just going to show you, as I said, we had a need that if I'm here, I need to know to go down. I know intuitively that that makes sense. As a human, I see it. But I need some kind of an algorithm or a technique. It just so happens that calculus has a tool for that. Given a function, so this is the function e, which looks like this one over here. You see that? That's the function of e. So then the notation is that I say the derivative of e, but I want the partial derivative because I'm only going to derive it in terms of that particular weight. Why just that particular weight? Because what if I have two weights? Then I also need it in terms of the other weight. And what about the bias? Then I also need it in terms of the bias. But we don't have to worry about that because that's a whole field of calculus called partial differential equations, basically. And so we're just going to take the derivative of a function in terms of its parameters. So what that means is if I had Y1, W1, W2, and the bias, I would do the derivative of E in terms of W1, find out what that is, and the derivative of E in terms of W2. And I find that parameter. That's the beauty of it. So you don't even have to worry about this. You understand that you need it to know that information. And it just, as a coincidence almost, it just so happens that Isaac Newton or whatever, when he was inventing calculus, he invented exactly the thing that they need. Okay? So what that gives you is what is called in calculus, it says that it gives you the tangent, basically. So that's now like that. So it gives you like, what is the line that touches that point in the curve and what direction does it have? Like what slope? And that slope is the information that you use. So for instance, if you take the derivative of this point in respect to the graph, it looks like that, you see? So they have opposite direction. So it gives you information now of kind of how it's sloping, and then you know which way is down. Do you guys see what I'm saying? That's the beauty of it. So let's say for the sake of argument, this is going to return plus and this minus. Got it? So the technique in calculus at this point in time just calculates this line, this slope, or that slope, and that turns out to tell you this plus or minus, which is relative to knowing if you're going to add, right, to the error or subtract from it. Does this make sense, guys? That's the whole idea of this. This was, so Widrow, what Widrow did is he derive this and arrived at the perceptron, but he couldn't figure out how to apply this to very deep neural networks. You know, like he could figure it out just for one layer, but he couldn't figure out for deeper layers. That's what Geoffrey Hinton, if you've ever heard of him at the University of Toronto, he invented with his team the algorithm stochastic gradient descent, which takes this idea but applies it to neural networks. But it's the same idea. Okay. But Widrow, if you saw in the notes, made this connection. Okay. So I have a curve, I have a point there, I need to go down. What mathematical technique gives me that? As it turns out, it is the derivative of a function. All right. Any questions so far? Making sense? We're almost done. Okay, so now you don't need to know calculus, but I will show you the mechanism here. Oh, I ran out of notes. Let me yeah, what I'm going to do is I'm going to start it again.